let's see the notation for showing the complexity, which is called BigOh notation. Now let's see the idea of BigOh notation first. In the formal definition is that given function fn and gn, we say fn is BigOh gn if there are positive constants that c and n naught, such that fn is less than or equal to c times gn for n greater than or equal to n naught. It looks quite conceptual. The idea is that c times gn will give the upper bound of fn. Now that is the main idea. If you find it too conceptual, okay, let's see this graph. It illustrates the BigOh notation. The fn is BigOh gn for fn is less than or equal to c times gn when n is greater than n naught. So you can see that c times g is actually give an upper bound of fn after n is greater than n naught. Okay, after this point, c times gn must be greater than fn. So if we find a function gn, then we will know that fn will not greater than c times gn. So now let's see an example. 2n plus 10. This is BigOh n. Why is it so? Because 2n plus 10 is less than or equal to cn for c equals 3 and n naught equals 10. Now remember, when we do a computation analysis, we are not doing the mathematics, okay, to try to strike c or n naught, but it will give you an understanding, okay, of the mathematical background about how we can implement this analysis of algorithms. The key point is there are positive constants c and n naught make the statement true. So it is illustrated in this graph that 3n is the dotted line. Okay, it becomes the upper bound. Okay, it becomes the upper bound for the line of 2n plus 10. Okay, remember it is logarithmic graph. So we read BigOh n as BigOh of n or order of at most n. So just give you an example, okay, before I go into detail. If an algorithm uses 6n plus 3 operations, it will require time proportional to n. We say it is BigOh n. If an algorithm has a time requirement proportional to n squared, we say it is BigOh n squared. Okay, give you a concept of the relationship of BigOh n and the algorithm. So now let's see more about the meaning for BigOh n in terms of the size increment and the value or the expression. For example, 7n minus 2. And what is the BigOh notation for it? If we try to calculate, because we can find an n, for example, and for example, if C is equal 7 and N not equal 1, then for this function, this function 7n minus 2 cannot be greater than 7n. Therefore, big O n is a valid expression. How about this one? 3 times n to the power crib plus 20 times n to the power 2 plus 5. So we know that it is big O n crib, because if we just assign C to 4 and N not to be 21, then this CG, that is 4 times n to the power 3 when n not, that is 21, then it must true that it is greater than this function. Let me restate that the value of C and N naught is not the main concern in the analysis of algorithm, but we would like to know about the upper bound, that is this function. As long as we can find this function, we can get the upper bound. That is what we are looking for. And let's see one more example. Okay, 3 log n plus 5. Then we will know that it is a big O log n, because we can find a C equals 8 and n not equals 2. Then the case will become valid. So at this point of time, if you are a bit confused about the calculation, don't worry too much, because okay, we will come across the actual understanding in computational analysis. But as you may observe that from the above calculation, you can see that the rules can be applied directly by some simple tricks. If it is a Fn polynomial of degree d, that is highest power of the variable, then Fn is big O n to the power d, that is to drop the lower order terms as well as drop the constants factors. So that is to use the smallest possible class of the function. For example, we say 2n is big O n, just n, instead of 2n is big O n squared, because the highest term is n, and use the simplest expression of the class, that is we use big O n for 3n plus 5 instead of big O n instead of big O 3n. So these are the basic rules. If we look at more example here, okay, actually it will show you some more cases. such as this one, you can see that the terms are encrypt and n times log n. Then encrypt should of the higher order. Therefore, it would be BigOh encrypt. If it is BigOh n versus log n compared with log n, then we know that the growth rate of log n is greater than the log n. Therefore, it would say BigOh log n. And also, you can see this example, 2 to the power 100. But actually, it is very large number. But because it contains no variable, so it is constant. Therefore, it is BigOh 1. So remember, BigOh 1 is actually representing a constant. Okay, for the last case, 5 over n. So we call it BigOh 1 over n. Okay. So because that is holding term of n. Okay, so with this, you can understand how can the function be represented in the BigOh notation.